Today we are doing the design for the inverting converter. 2 videos ago we did the schematic capture and the component calculations. So obviously if you want to know how we got to this circuit, you can watch part 5 of the Let's Design a Power Supply series, which I've got on YouTube. So the main aim for today is to design the footprint for this component here. So that's our coupled dual inductor. And then go on to do the PCB design for this inverting converter here. So let's get started. The part number for the dual inductor is GRQ74, and this has the recommended pad layout as shown on the screen now. So this is what I will be trying to recreate for the footprint. And obviously we have the sizes on here. One of the things I cannot see in terms of dimensions, so obviously we've got 7.6 over here, but I cannot see what the maximum dimension on this side is. I assume it's a 7.6 as well, just because this obviously you got 6.1 dimension over here. So in order to design a new footprint, you basically need to go into footprint editor in KiCad. So I'm using version 8 over here. So go into footprint editor. Once the footprint editor is open, I will scroll down to the library that I created last time. So I called it my library. And in there, I'm going to right click and click new footprint. For the name of the footprint, I am basically going to copy the part number of this part. So DRQ74-2R2-R. And it is an SMD type footprint because it's an SMD component. So to put down a pad, you basically go over to here, add a pad, and click in the location that you want it. And then you can double click to select that pad. From the recommended LAN pattern, I know the size of the X dimension needs to be 1.73 and the size of the Y dimension needs to be 1. The component itself is obviously 7.6 by 7.6. So what I'm going to do is make a courtyard that is basically that dimension. So 7.6 and 7.6. And the starting point, I want 7.6 divided by 2. And the end point, I want 3.8, as you see the calculation there. And because it's a square, it's going to be 3.8 everywhere. So the minus on the start points. So we've got our one pad now. I'm going to put down pad number 2, which is down here. Pad number 3, which is over here. And then pad number 4. Now the dimension from here to here should be equal to the dimension down to here. So you see we've got 3.8, 3.8, and 3.8 square basically. For the location of the pad, we've been given a dimension where we need to be in the Y direction. I need a 0.4 gap between the two pads. So obviously to do that, I need to calculate the size of the pad, which is 1. And obviously the location that we see on here is the center. So the pad size is 1. The clearance between the two pads is 0.4. I need to add a space of 0.5 plus 0.4 divided by 2. So we have a pad Y location of 0.7. And then pad 2 will be just the same in the opposite direction. So now we should basically have a 0.4 gap between these two pads as recommended in the data sheet for the component. Next, we have a distance between the edge of this pad to the edge of this pod, and it's been given to us as 7.9. So again, doing the same calculation as we have the center location on this Y direction. So the distance between the two pads is going to be 7.9 minus 1, so 6.9 divided by 2, as we obviously have it on one side and the other side. So this will be minus 3.45. And if we measure the distance between the two pads, we should get 7.9. We didn't because I took the wrong dimension. So the X direction is 1.73 rather than 1. So what I need to do is minus 1.73 from 7.9. So let me just redo that calculation. So 7.9 minus 1.73, and then that basically divide by 2, and this is the dimension I should have for the clearance. Now if I measure this, you can see I've got a distance of 7.9 edge to edge on the pads. Now just to bring this back on, you can see I've got 1 millimeter by 1.73 pad. So just to confirm that, I've got 1 by 1.73. Obviously, we looked at the clearance between the two, which is 0.4, and the edge to edge distance, which is 7.9. The last thing I'm going to do is add some indicator for pin 1 orientation. So for that, I'm going to use the silkscreen layer, which is on F silkscreen, basically front silkscreen. So 1 to 3 is inductor 1, and 2 to 4 is inductor 2. So I'll make sure my schematic follows that as well, otherwise I'll need to change that. So 1 to 3 is inductor 1, and 2 to 4 is inductor 2. First of all, I will just add in a silkscreen to show the edge of the component. So you can see I've completed the footprint for this part. So I'm going to press the save button now, and I should be able to select this on my component selection tool. Let's go back to the schematic editor, select the component selection tool or footprint assignment tool, and then I will go into the coupled inductor, find my library on this side, and then click this button here basically. So apply and OK. So we've got that. Everything else was already selected because we did that on the video part 4. So next I'm going to go into the PCB editor, and what I'm going to do is basically update the changes from the schematic. So you can see I've got my inductor now. You can see I forgot to move the references and everything that I moved out initially, but that's fine. I can update the footprint at a later time if I need to. First thing I'm going to do is open up my board so that I have a bit more space to work with. I will basically now put the components in roughly the right place by following the schematic layout. So from the schematic, we should be able to get a rough approximation of where I need the components to be. So obviously in the schematic, you can see the inductor is above the regulator IC. Then we've got C24 here, D4 on the side, got all the feedback network and the output capacitors on the right hand side. We've got the input capacitor on the left hand side, and then we've got some of the kind of the function components on the bottom. So soft start, frequency timing, things like that. So I'm going to arrange it in roughly this layout on the PCB design. As I said before, getting the component layout right makes the tracking a lot easier. Now, one of the things I can see on this is I need to update some of these components because they all seem to be 0805s. So I think I've assigned the wrong footprint to them. So going back to my bill of materials for this part, from the bill of materials, we can see the 22 microfarad capacitors, which is on line 6. They are 0805, but pretty much everything else is 0402. So I'll find out where the 1 microfarad and the 1 nanofarad capacitors are, if any, and make sure to change them to 0402. Open the PCB design again and update the PCB design with changes we just made to the schematic. At this point, it might be a good idea to have the schematic and the PCB design side by side. So I've got C24 I need. But placing the components properly is one of the most important things when doing a PCB design. So if you do this correctly, it will simplify when you do the tracks. So now I'm just going to cut to some music and lay out the tracks. Sit back and enjoy. So I've done the PCB design. I'm a little bit unsure about the feedback track that's going from here to here. I'm considering if I should run it from here, but obviously that's going right under the switching node, which is high, which may have a lot of noise. I don't want to take it down through the ground path here because I want to have some wires on this section so that I can connect the chip and the ground to the ground plane, which is on layer 2, the green layer that you see here, which will extend down all the way to here basically. See, I've got a few more episodes before I order this, so if you have any feedback for me, please let me know. So now I have completed the PCB design for the inverting converter. There are a few things I'm a bit unsure about, especially this feedback track over here and the labeling of this silk screen, but I'm limited for space, so I think this will be okay. I'll think of a way if I can add any more clarity to the silk screen for this part. Other than that, it looks like, you know, the PCB design is complete. I've got easy access to 12 volts, which I will need to put some header sockets on here. I've got easy access to 24 volts over here as well, so I'll put some header sockets on that. And then the last thing I need to do is basically configure the layout and do the 3v3 buck converter on this as well. Then we can finally order the parts. So it will be good to test the PCB on video and I'll record my findings. Obviously, I've tried to get as much flexibility as possible on this, but one of the things I really want to test is how much current capability I have with the rechargeable battery, with the 4 AA cells and the 5 volt USB. What would be ideal is if I could add a USB-C power controller to this chip, but I think I'll save that for another project. So just to finally show you what this looks like in the 3D viewer, you've got the inverting converter down here. You've obviously got the boost converter down here doing 24 volts positive. You've got the buck boost converter doing 5 volts. This will be connected to the rechargeable battery and the 4 AA cells. And you've got the 5 volt USB. This, I want to basically have 5 volts going to these two ports. And I will add a switch that can select either the supply from here or directly from the USB. So obviously this part will be used when we have 4 AA cells or the rechargeable battery. So I think I will need to move this down here and I'll move the USB-C connector down here somewhere. For the output connectors, I'm thinking to just use banana plugs, as I have banana plugs available or banana plug wires available to use as power supply leads. One last thing that I need to do for the next video is the 3.3 volt buck converter. In 2 weeks time, I will have ordered this part. So obviously if you do have any feedback for me, especially with this feedback route here, I'd appreciate that. Thank you. That's all I have to share for today. So thank you for watching my video and don't forget to like, comment and subscribe.